Good morning. Now we are discussing the Huygens explanation of double refraction. Huygens, in order to explain double refraction, makes use of two or proposed few postulates. So according to his theory, when light wave is incident on the surface of a doubly refracting crystal, each point on the surface will be the origin of two secondary wavelets, and those two secondary wavelets are ordinary and extraordinary, and these ordinary and extraordinary secondary wavelets spread into the crystal. This is the first theory of Huygens. Now, the second point is the wavefront corresponding to ordinary wavelets travel with same velocity in all directions, and therefore the wavefront corresponding to it is spherical. Since ordinary wavelets travel with same speed in all directions inside the crystal, the wavefront corresponding to ordinary wavelet is spherical, as shown in figure 1 or figure A. And as the extraordinary wavelets travels with different speeds in different directions, therefore the wavefront corresponding to extraordinary wavelet is an ellipsoid of revolution, as shown in figure B. This corresponds to ordinary, first one, second one corresponding to extraordinary. And the fourth point, the sphere and ellipsoid will touch each other at points along the axis of the crystal because along the optic axis, since both ordinary and extraordinary rays travel with same speeds, and therefore they touch each other along the optic axis of the crystal. And in case of negative crystals, sphere lies inside the ellipsoid. As shown in the third figure. Sphere is inside the ellipse. Also, in positive crystals, sphere lies outside the ellipse, as shown in figure D. Sphere lies outside the ellipse, or ellipse lies inside the sphere. Right? These are the postulates used by Huygens in order to explain double refraction. Now, coming to the Huygens construction for double refraction in uniaxial negative crystals. We are considering uniaxial negative crystals. In uniaxial negative crystal, we study double refraction by making use of Huygens theory. We consider calcite crystal, which is uniaxial negative, and we also consider a plane wavefront. Right? Now, the first case is we have considered the optic axis in the plane of incidence. Also the optic axis is inclined at an angle to the cut surface. This is my cut surface, xy is the cut surface, and for this cut surface, the optic axis is inclined at an angle. Now, the incident rays are oblique. We have considered oblique incidence. These two are my incident rays, and these two incident rays are obliquely incident on the cut surface xy, right? And in this, AB represents the plane wavefront. Now, by the time B reaches the surface of the crystal at C, A will send two waves, ordinary and extraordinary, inside the crystal. Now, distance traveled by the ordinary ray in this time In this time, in the sense, when if t is the time taken by light to travel from B to C, then in this time t, the distance traveled by the ordinary ray at A inside the crystal is. Therefore, that is V0 into T. V0 into T. And V0 into T is nothing but equal to BC by C. Time is distance traveled by the speed of light. Distance traveled is BC, divided by C is speed of light, and therefore this can be written as BC whole divided by C by V0. Or C by V0 is nothing but N0, refractive index of the crystal for the ordinary ray. Similarly, distance traveled by the extraordinary ray is equal to VE into T during the same interval of time. That is equal to VE into BC by C, or that is BC whole divided by C by VE, or that is equal to BC by NE, where NE represents the refractive index of the crystal for the extraordinary ray. The tangent drawn from point C to ordinary wavefront, or in other words, the circle or sphere, gives ordinary refracted wavefront. Similarly, tangent drawn from point C to the sphere to the ellipse or extraordinary wave surface gives extraordinary refracted wavefront. You can see in figure, right? Similarly, AO represents the ordinary ray and AE represents the extraordinary ray. AO represents ordinary ray, AE represents extraordinary ray. Similarly, this represents, for the same crystal having an oblique optic axis, and the incident ray is normal to the surface. So it is normal incidence. AB is the plane wavefront. This is CD. CD represents the ordinary refracted wavefront. CD represents ordinary refracted wavefront. This is FG. FG represents the extraordinary refracted wavefront. Similarly, these two represents the ordinary rays, and these two represents the extraordinary rays. Now, the second case. The optic axis is in the plane of incidence and parallel to the refracting surface. The optic axis in this case is parallel to the refracting surface. These dotted lines indicate the optic axis, right? And in the first case is corresponding to the oblique incidence. So you can see here there is double refraction. AB is my plane wavefront. CD represents ordinary refracted wavefront. CF represents extraordinary refracted wavefront. AO represents ordinary ray. AE represents extraordinary ray. There is double refraction, you can clearly see. Whereas in case of normal incidence, AB is our plane wavefront, incident wavefront. Then this line CD represents ordinary refracted wavefront. FG represents extraordinary refracted wavefront. AO, AE are along the same direction. Though they are along the same direction, there will be double refraction because they are traveling with different velocities, different speeds. Though they are in same direction, their speeds will be different. Therefore, there will be double refraction. This is the case of normal incidence. Now coming to the optic axis perpendicular to the plane of incidence and parallel to the refracting surface. It is parallel to the refracting surface and perpendicular to the plane of incidence. This dots now represents the optic axis perpendicular to the plane of incidence. Again, this is the case of oblique incidence. AB is my plane incident wavefront. CD is the ordinary refracted wavefront. CF is the extraordinary refracted wavefront. AO is the ordinary ray. AE is the extraordinary ray. So I can clearly see the double refraction. Second case is the normal incidence in this. Again, AB is the plane incident wavefront. CD, FG are the ordinary and extraordinary refracted wavefronts. AO, AE, BO, BE are the ordinary and extraordinary rays. Though they are traveling along the same direction, there will be double refraction because the speeds of the ordinary and extraordinary rays are different. Now coming to the optic axis in the plane of incidence and perpendicular to the refracting surface. This is my refracting surface. The optic axis is perpendicular to the refracting surface and is in the plane of incidence. For oblique incidence, you can see clearly there is double refraction. But for normal incidence, both the rays, ordinary and extraordinary rays, travel with same speed in same direction. In the sense, there is no double refraction. As we know that there is no double refraction, both ordinary and extraordinary rays travel with same speed when they are traveling along the direction of the optic axis. So, the rays are parallel to the optic axis in the sense they are traveling along the direction of optic axis, or they are parallel to the optic axis. So, there is no double refraction. Hence, they are said to be merged. Thank you.